So in this problem, we're doing a setup with a spring that is attached to a 1/2 kilogram mass. So 1/2 kilogram. We know that when the spring is stretched out from, say, 0. So from its, if that's its equilibrium position, we know that if the spring is stretched out 2 meters, it gives us a force of 100 newtons in that direction. So on the end we have a 1/2 kilogram mass. We are given the initial conditions x0 equals 1 meter and v0 equals -5 meters per second. So this distance is only 1 meter, and this is moving at the very beginning. It's sliding this direction at 5 meters per second in that direction. So we can set up a differential equation for this pretty simply. If we remember, I think it's Hooke's law, which is that the force applied by the spring is proportional to the distance from its equilibrium point. We can find the spring constant using the fact that when it's stretched out 2 meters, it applies 100 newtons of resistance. So 100 newtons equals 2 times k. The spring constant divided by 2, k is 50, right? So what we have is the mass times the acceleration, m times x double prime, the force, is equal to negative kx, the distance from the equilibrium point. That makes sense. Rewrite it as mx prime plus kx equals 0. Divide over the m, so x double prime equals k over m, x, or not plus, equals, not plus, equals 0. And now we are just going to solve that, which should be pretty simple. And we can just kind of look at it and know how to solve it. So that's going to come out to a constant times sine, or cosine, nope, not sine, cosine, of, or let me write this, x of t equals of the square root. I'm going to get on this side. I'm in kind of an awkward position because I can't cover the front. I don't want to be in front of the writing. The square root of k over m t plus b, another constant, sine of the square root of k over m t. The reason I know this is, well, it should be pretty simple. So let's start just with the cosine. If you take the derivative of the cosine, you'll get negative sine and then times that k. So when you do that twice, you get the second derivative. You have the square root times the square root. You just get the k over m. Negative. And same thing with the sine, and since they are both linearly independent, you Just add them together like this to get the general solution. Okay, so now we need to get A and B. We need to find out what A and B are. And we can just use these initial conditions. So x of 0 is 1. 1 equals cosine of square root of k over m times t. So k is 50. Let me write that down. K equals 50, because I'll know it. K is 50, m is 1/2, so that's actually just square root. That's just 10. That's square root of 100. That is 10. Let's write that. And the same thing over here. Where's it? Yeah, okay, so cosine of 10 times 0, that's cosine of 0, that's 1, so A. Sine of 10 times 0, sine of 0 is 0, so B is irrelevant, so A equals 1. And then for B, we need the derivative of that, because we're dealing with velocity now. So I'll just write that out real fast. X prime of t equals 10 or negative 10a sine of 10t plus 10b sine of, or cosine of 10t. So that is negative 5 equals, so a sine, so that's 0. This whole thing is 0. This thing is going to be 10 times b, because that's 1, so 10b. Negative 5 equals 10b. B equals negative 1/2. So what that leaves us with is x of t equals cosine of 10t plus negative 1/2 sine of 10t. So for the first thing we can find out from this instantly is we can find out the circular frequency. So the way this is going to work out, so when you are adding a cosine and a sine, when you add them together, you get another. So obviously we all know cosine is a and sine are the same function. There's a crude scratch. The same function transposed over, right? When you add together cosine and sine, you get another one of these functions transposed some amount and widened or squished or squashed some amount. Although actually I shouldn't have done that with my hands. It is never going to be squashed or squished this way. So we can say for certain that this 10, these 10s, that's the circular frequency. So that is going to take it's going to be if you imagine an angle going around a circle like this, right? That's just all cosine is or sine is, it's the component of the horizontal or vertical component around a unit circle. If this is moving like 10 radians per second, right? So that's what that means. That 10 means this is moving 10 radians per second. In fact, that's all that a spring is I like to think of it as going back and forth. And I like to think of it like it's going in a circle, and then you're compressing it down. So that's what I mean when I talk about the circular frequency, or I guess the circular velocity would be a better word. The angular velocity, it's not the actual velocity of the mass, but it's the velocity of the mass if it was moving in a circle. So, anyway, from this, we can instantly tell that, and it's represented by the letter omega. Omega equals 10. Tell that instantly. And from that, we can figure out the actual frequency and actual period. So, the period, let's think here. So this is 10 radians per second, and the period is how many seconds it takes, right? So it's 2 pi radians to go around once, and this is 10 radians per second, so 2 pi divided by 10. So, yeah, okay. The period equals 2 pi over 10, which is equal to pi over 5. The frequency is 1 over the period. So pi over 5 seconds, or let me get that in a number, so that kind of has a framework, because I don't know how long pi over 5 seconds is. Okay, I'll go more than half. So around 0.628 seconds. The frequency, 1 over that, let me see, equals 5 over pi, 1.592 hertz. So that's the period and that's the frequency. I'll erase that because I'm running out of room. The next thing we want is the amplitude. And the amplitude, the way that you get it, and I'm going to make a separate, an add-on to the very end explaining why it is this way, but the way that you get it is you imagine a triangle, right? This is important information. You imagine a triangle with an angle here, a right triangle with an angle there, that is alpha, and then this leg is A, this leg is B, and this leg is C. And as it turns out, C is the amplitude. And when I first saw this, I thought, okay, maybe A and B are like, maybe rotate. No, it's not quite. But I'll explain it later. But we do need to find C. So in order to get C, it's just A squared plus B squared. So our square root of A squared plus B squared. A squared is 1. B squared is 1/4, 1 1/4, 5 quarters, square root of 5 over 2. So C equals square root of 5 over 2. So that's the amplitude. Now we need to find alpha. So alpha is called the phase angle. And what that is imagine you have 2 clocks. Like, you have 2 clocks going, right? And they're going at the same speed, but one of them says it's 1:30 and the other one says it's 1, right? So the phase angle is how far offset it is at the beginning, or how far offset it is from kind of like the standard, right? So this phase angle is how far offset, and going back to the idea of the, let me go back to the idea of the spring as really rotating around a circle. When I start off, right, if I started it right here, the phase angle would be right there. That'd be alpha. So let me explain what that's used for. When you release the spring, you don't, because I have an initial velocity, right, because I have a little bit extra velocity, it's gonna come back a little bit farther, right, around the circle. It's gonna, there's more to be gone over here. So the phase angle tells us how far from the final part we're starting. And the phase angle is also used for something called the time offset, which is represented with delta. And I'm gonna, in order to explain that, I'm going to have to draw a little diagram. I promise I'll get back to this soon. Back to the math soon. I guess this is math. Back to actually making progress on the problem. If I have this, I have, okay, so y-axis, x-axis, and then I have some function like that, right? So, from here to here, that's the period. That's the period. From here to here, that's the or lag time, I believe. So the lag time is like a cutoff period. It is until you get to the beginning of where the periods start going. Maybe it would look a little bit better if I drew it a little bit differently. Let me see here. What if we start down? So we go like this, up, down, up. Okay, so from here to here, that's the period. From the beginning of the graph, from 0 to the first hop, for the first hop, that is the delta. That's the lag time. So back to calculating alpha. Alpha is the phase angle. Calculate alpha, as you hopefully remember right before I erased it. Alpha A, B, and C. Alpha is just going to be the arctangent of B over A. So let's see, what's B? Negative 1 over 2. A is 1, so that's an arctangent of negative 2. Except it's not just the arctangent of negative 2. If I had the arctangent of negative 2, I'll draw another unit circle. If I had the arctangent of negative 2, let me think, pi over 2 is, okay, so negative 2, that's somewhere around there, right? Negative 2. Not the arctangent of negative 2, arctan negative 2. Whatever angle. So it's not. Well, regardless. If I had some arctangent of a negative number, so something down here, right? It would be a negative angle, because it's just going to go that way. What we want is a big positive angle. We want this whole thing. So the reason that we want that is because if you just have a negative angle and then you try and calculate the lag time with that, it's going to imagine the way you're doing the math is you're assuming that the spring is going to go back this way, which it's not. It's going to go forward and then it's go back and it's going to go forward. It's not going to go backwards. The spring's pulling on it. So we need to do 2 pi minus, because it's in this quadrant, because we know because B is negative and A is positive, because we know the angle is somewhere in this quadrant, we need to do 2 pi minus that angle, which will give us the whole thing around, if that makes any sense. So 2 pi minus arctangent of negative 2. Arctangent of negative 2. That's about 7.39. So or excuse me, 2 pi plus. 2 pi plus the arctangent. Arctangent of negative 2. 5.17. 5.176. So alpha equals 5.176. Okay, so now that we have the amplitude, we have the angular velocity, right? We have this part, we have the amplitude, and we have the phase angle, we have the offset. We can just write this as a cosine angle, right? So we can just rewrite this as x of t equals square root of 5 over 2 c times cosine of 10t plus 5.176. Or, no, there's, yeah, okay. So that's the final position function. Now, the last thing to do is to find the lag time. Finding the lag time is incredibly easy. So the lag time, we have delta, that's how many radians per second. We have radians. Lag time is how long it takes to get to go the phase angle. So we have radians per second, radians. So radians over radians per second is going to give us seconds. So the lag time in delta, or in seconds, delta equals radians over radians per second, alpha over omega, which is 10 divided by 5.176, which is roughly 1.932. So that's how you, I guess, analyze very basic undamped motion of a spring. All right, so this is like my 4th or 5th attempt, and every time I'll be working on it, and I'll get halfway through, and I'll forget something really stupid, like a couple of times I just forgot like the word proportional, and I just sat there for 10 minutes looking like an idiot. So I'm gonna try and do this in one take. So example 2 is just like example 1, same initial conditions, same K value, same mass. The only difference is there is a resistance. So for every meter per second that the mass is moving, there is a 1 Newton resistance in the opposite direction. So if it's moving this way, 5 meters per second, there's a 5 Newton resistance. If it's moving this way, 10 meters per second, there's a 10 Newton resistance. So let's write that out. The mass times the acceleration, the force is equal to negative kx. So that is the position times the spring constant, the position away from the equilibrium, plus x, the velocity. Since it's 1, it's just the velocity. So, negative kx, so this way, plus a little bit that way. This way, plus a little bit that way. So, let's just write that out as x prime plus negative x prime plus kx equals 0. You can plug in 1/2 kilograms for the mass. We can plug in, we don't have to plug anything here. And we can plug in 50 for K. Now, I'm just going to, let me go pick a 5. That looks like 80. Multiply this out just to make the characteristic equation simpler. Okay, so now we just have a linear second degree differential equation. In order to solve that, we're just going to make the characteristic equation r squared plus negative 2r plus 100 equals 0, r standing for root, of course. Now we have to find the roots of this, and in order to do that, I'm just going to use the, I forget what it's called, the one we've known since algebra, the x 2 minus the root of 4 minus 400 all over 2. So then, I'm just going to simplify that to 1 plus or minus square root of negative 99, which is equal to 1 plus or minus I square root of 99. That's not the root, that is 0. So the root is just negative of the 0 times minus 1. So our root is negative 1 plus or minus square root, or I, times the square root of 99. And when you have complex roots, you do the, when you have a pair of complex roots, it's e to the first, the real part times t, times, well, you'll see. You remember last lesson when we learned this. So x of t equals e to the negative t times a cosine of square root of 99 t plus b sine square root 99 t. Now we just need to find a and b. In order to find a and b, we just need to use the initial conditions. So x0 equals 1 and v0 equals negative 5. So x0. X of 0 is 1, so 1 equals e to the negative 0, that's just 1. Cosine of square root of 99 times 0 is cosine of 0 is 1, so a. Sine of square root of 99 times 0 is sine of 0 is 0, so the b gets irrelevant, so a is 1. To find b, we need to use second v0 equals negative 5, so in order to do that, we need the derivative of this. So let me do that real fast. So first part, this is the derivative of the second part. You'll remember this, of course. Okay, so that's the first part. The second part is this times the derivative of that. The derivative of that is just negative that e to the negative t, and the derivative is negative e to the negative t. So we can just add minus x of t to the end. So negative 5 equals e to the 0, so 1. Negative square root of 99 times a times sine of square root of 99t. Is, so sine of square root of 99t, that's sine of 0, so that's irrelevant. Square root of 99 times b times cosine of square root of 99t. T is 0, so that's cosine of 0, which is 1, so negative 5 equals the square root of 99 times b minus 1, because x of 0 is 1. Add 1, negative 4 equals square root of 99 times b. b equals negative 4 over the square root of 99. Now we just have to go over here and plug that in. God. Actually, not yet. We're not going to plug that in yet. We're going to do that later. Or actually, we're never really going to plug it in directly into that. What we're going to do is we're going to find the, so this part, we're going to find it in the form of C times the cosine of the omega 0 times or plus alpha. So for the circular frequency, that's just going to be, okay, so sorry about that. My phone has a buzzer that goes off when it's time for class, and I'll hate the government habit. So we were talking about getting the circular velocity, the radians per second, because so the way again, and I explained this earlier, it's like a flattened circle, so the radians per second. So that's omega 0, and pretty clearly see it's going to be square root of 99. It's going to be this number right here. Whatever the time is multiplied within the trigonometric functions, it's going to be that. So let's write that out. Square root of 99. So the reason we need that, we're looking for something called the pseudo frequency, the pseudo period, and the changing amplitude function. So the pseudo frequency and the pseudo period. Let's look at this. So this is right here. This in the parentheses is a normal spring function, I guess. It's not the spring function if there wasn't dampening, but it's a spring function. And then this e to the negative t, that's going to start out at 1 and 0, and it's going to go down, right? It's being multiplied. So what we end up happening is we have, I'll draw two. I'll just draw it here. So we have one function, right? And then we have this squeezing. What that looks like is, so it try to be accurate. So it gets squeezed by various amounts. It gets compressed down as we go. However, you'll notice, since all we're doing is multiplying it, it's going to have the same frequency, the same period, right? Just squished, and it's not called a period because it never repeats. It gets smaller, but it's called a pseudo period because anybody who has two eyes can tell that it's the period essentially. So the pseudo period is just the period if we ignore this. So, and let me think there, that would be the period is going to be the 2 pi divided by omega, the radians per second, so 2 pi radians divided by radians per second. That's going to give us seconds. So equals 2 pi over square root of 99 seconds, or about 0.631 seconds. And then for the frequency, that's just going to be 1 over the period. So that's going to be omega over 2 pi. It's going to give us 1.5. Oh God, 5 0.84 about hertz. So, okay. Hearts. And, okay. So those are the pseudo frequency and the pseudo period. And now I want the changing amplitude function. I'm just gonna erase this. I just want to know how to do it. The changing amplitude function is, again, it's the same kind of principle. We had this decreasing, this normal wave that's being squished as we go, but the zeros are all the same, so it lines up, right? And you can imagine that for every hill, there's a corresponding hill that gets smaller and smaller and smaller as you go. And if we know the height of this hill, what if we want to find the height of the corresponding hill? We just want to, what we essentially want to do is we want to find the amplitude of this internal wave and then multiply it by the scaling factor. So it's that simple. So we remember that the, and this is, well, hold on this. We remember that the amplitude is C, so if A and B are on a triangle. Can you see this over here? Yeah, okay. I'm just trying to make sure. Okay. We have A, B, and C. And we have alpha. So we'll remember that A, B, and C are on a triangle. Alpha is the offset angle. So again, it's like it's going in a circle and it's been squished down. Alpha would be the offset as to where it starts. And this should make sense because it's B times the sine, A times the cosine, so A times the cosine, B times the sine. Yeah. So because it's sine of 0, 0, 1. So we need to find C. That is that's the amplitude. So C in this case, square root of A squared, so 1, plus the square root of B squared, so that's 16 over 99. 1 plus 16 over 99 is C equals square root of 115 over 99. But the amplitude, the changing amplitude of T is C times the dampening function e to the negative t. So that is simply e to the negative t times square root of 115 over 99. So that's going to give the amplitude of the wave at any given point. Now, we have to find alpha, the offset. In order to find that, I'm going to have to pull out my calculator because let me put it into, I was using it for physics, so it's in degrees. Give me a moment. Okay, back in radians. I want to find, we're going to use A and B again, so alpha equals arctangent of B negative 4 over 99, square root of 99 over A. So and this is actually important to realize. So B is negative and A is positive, right? So, good Lord. Didn't mean to drop that. So B is negative, so it's really like this. So if I have a unit circle, here we go. Right, so alpha is there. There we go. it's going to be in quadrant 4, which means that alpha is negative. So I believe it is just arctangent, but that's just necessary. You might have to fiddle around with it to get the proper, what alpha should be. Okay. Alpha is about negative 0.3822 radians. So now we have C. We have, or C here, we have alpha and we have omega. So we can get the position function. We have these are all of this interior wave. So we can get the position, the updated, I guess, position function of the interior wave and multiply it by e to the negative t to get the final position function. So I'm going to do that right here. T equals e to the negative t. I hope you all can see this. Yeah, okay. Times C 115 over 99 or square root thereof times cosine of omega square root of 99t, so t square root of 99 plus alpha, or negative 0.3822. All right. Now we need to find the time lag, I believe. So that's going to be how long it takes until it's back down, or how long it takes until it gets to 0. So to do that, and it's called delta. It's spelled delta. So I think it might go. It's that way. Delta. Oh, that's a 5. Equals. Let's think about this. So I want to find out how long it takes to do this distance, going that many radians per second. So square root of 99 radians per second. We want seconds. So we take radians divided by radians per second. So delta is alpha over omega. And then that is simply delta 5 again. Delta the time lag, that's another 5, is equal to, pull out my calculator, or actually I should say, because you can't have you can have a negative time, but it's going, yeah, okay. Divided by square root 99. 0.038, or yes, 4-ish seconds. I think that's everything. Okay, so I just realized I messed up. Right here, alpha's not negative. It's actually just really big. So what I should have done is, if you have the idea of the spring, right? The spring here, or actually no spring, and I'll explain why I messed up, so you don't mess up the same way. If you have the spring and then the objects, and then let's say this is the equilibrium point, so it's right? it's really moving, or it's not really moving. We can imagine it's moving. Oh, I don't think you can see me. No, you can, okay. You can imagine it's moving on a circle instead, right? Around and around and around, and then we just flatten it down so it's going back and forth. That's just cosine, of course. When you have the offset angle, right? Let's say the offset angle is here. It's going to go back towards the center first. Obviously, the spring is pulling on it. I had the offset angle here, right? This is roughly where alpha is. So, I had it. What it should do is this, let's think about it. It should go this way, and then back this way, and then back this way, and then back this way, and then this way. What I had done when I had negative alpha, and then I put these on, is I said, no, it'll just go this way. Obviously, it's not going to go this way, this way, this way, this way. It's going to go this way. It's going to go towards the, it's going to go with the spring. It's not going to, the spring's not pushing it out. So, what I should have instead done is I should have said alpha equals 2 pi minus, or it's negative, so 2 pi plus arctangent of negative 4 over root 99. And if you do this, you get something different. You get 5.9009 radians. So that's very different. And then you gotta do plus 5.909009. And then in order to get the offset, we have to do delta equals alpha over omega delta equals 5.9009 over square root 99. Which is equal to 0.593 seconds, about. So when you release this, it's going to take about a half a second for it to go all the way back around. So there's a little bit more about dampened springs I did not touch on. So what we just saw is an example of an underdamped spring. And what I mean by that is, if you remember when we solved it, we had an imaginary root, so there was a trigonometric aspect of the solution. So what that means is it did not repeat, but it did infinitely go over and under and over and under. It did approach zero. However, there were infinite zeros, right? Because of that trigonometric aspect. You could imagine, though, what if the dampener was a whole lot stronger, right? Maybe even a little stronger. We'll see. What if the dampener was stronger and it never? I mean, it might even go under. Might go under, right? But it doesn't have. It has only 1 0. Right? It only has 1 0. It does not repeat. There's no trigonometric aspect if it was dampened enough, right? That's a either overdampened or critically dampened spring. Now, an overdampened spring is one. Let's say we were like, okay, fine. I don't want to have a trigonometric aspect. I want it to settle down. What if I just got the biggest, most expensive dampener I could get? Well, you're wasting money because the critically dampened case, the critically dampened spring would be the spring that is perfectly dampened such that it does not. If it was just a little bit less, there would be that trigonometric aspect. It would go up and down over and over and over. It's perfectly dampened, so it's right on that line. So I'm going to imagine that we have our setup, and for some whatever reason we want to have the spring critically dampened such that there's no oscillation. It only crosses either once or none. So let's just set it up. Mass times velocity, or mass times acceleration, m times x double prime equals negative kx plus cx prime. M is 1/2 kilogram. X double prime. K is 50, and the c, well, the c is arbitrary. We're gonna solve for the c. Plus k, or 50x. Now, what's important, again, is to remember the initial conditions, and I forgot to write them down this time. x0 equals 1, and v0 equals -5. So we're going to keep those initial conditions. So with this, so we're just going to multiply this 1/2 into everything else. So x double prime plus -2 cx prime plus 100x equals 0. You get the characteristic equation r squared plus -2cr plus 100 equals 0. Now, when we get a root, there's obviously two, right? There's non-repeated roots, there's repeated roots, and there's complex roots, complex repeated roots. And those have 3 different forms of general equation, right? So we know that when it's a non-repeated root, like let's say there's 2 roots. Let's say there's 2 roots because we have a second root. There's 2 roots. It would be x of t equals a e to the r1t plus b e to the r2t, right? When it is a repeated root, there's only one root, it's x of t equals e to the rt multiplied by e to the r, or multiplied by a plus bt. And when there's a complex repeated root and there's 2 complex roots, you're gonna have x of t equals e to the real aspect of the root times t plus or multiplied by a sine of the or a cosine of the imaginary aspect of the root times t plus alright, let me just use I of times t plus b times the sine of imaginary aspect of the root times t. Okay, so that's what we just did. What we're going for is we don't want this. This has a trigonometric aspect, right? We do not want that. We'll find we're gonna want one of these two, right? One of these two. And actually, we're going to get this one with the critically dampened. So what we're going to do is we're going to shoot for the smallest c that does not give us a complex root. So let's plug it into the quadratic equation. Let me use the other side since this one is starting to get a little bit dry. R equals 2c plus or minus the square root of 4c squared minus 400 over 2. Factor out the 4, square root, so it's 2. Multiply the 2's, that is c plus or minus the square root of c squared minus 100. Correct. So that's not c plus this c plus or minus, that's not actually the root, that's a 0. The root would be negative c plus or minus. So what we've gotten here now to do is find the value of c. So the smallest value of c, so this is not going to be complex, is going to be 10, because 10 squared minus 100 is 0, so we need to find the 0 of this, right? So c equals 10, right? C equals 10, which means c plus 0 is also equal to c minus 0. So we have a repeated root. We have c twice. So the general form is x of t equals e to the 10t multiplied by 10, or by a plus bt. And a and b are constants. Now we just have to solve for a and b. So to solve for a, plug in x of 0. 1 equals e to the 10t, e to the 10 times 0, 1. A plus b times 0, a equals 1. This we use, I don't know this pattern here. A equals 1. For b, we need to take the derivative. So x prime of t equals 10e to the 10 t, 10e to the 10t. Or actually, no, not correct. Not right. Incorrect. I'm going to multiply it out first. Just to, because I don't want to have to do the product rule when I don't have to do the product rule. I'll have to do the product rule once, but I don't want to. Oh no, never mind. X prime. So, right t left. E times e to the 10t times the derivative of this is just b. So b e to the 10t. Plus left d right. 10 e to the 10t a plus bt. A is 1. Let's just replace that. X prime of 0 is negative 5. Negative 5 equals 10 to the 10t. So that's 1 equals b equals 10 to the e to the t. That's 10 times 1 plus bt. So 10 plus, well, bt is 0, so plus 10. Subtract 10, b equals negative 15. Okay, now, finally, in the critically dampened case, x of t equals e to the 10t times 1 plus negative 15. Oh, that's not a good 5. Negative 15